Hi, my name is Rohit Agarwal, and I am here to present our paper, Auxiliary Network, Scalable and Agile Online Learning for Dynamic System with Inconsistently Available Inputs. Deep learning models dealing with streaming data assume that the dimension of the inputs at each time instance is fixed and same. But this is not true for many real-life applications like autonomous vehicle, modeling the behavior of mitochondria in a cell, which can lead to drug discovery. For example, a cell can have thousands of mitochondria, and consider each mitochondria as a feature. Some of the phenomena that can occur are touch and run, where you have two mitochondria 1 and 2 at time step t equals to 1. Mitochondria 2 starts moving towards mitochondria 1 and touches it, giving us a new mitochondria 3 at time step t equals to 2. Further, this mitochondria 2 moves away from mitochondria 1, giving back 1 and 2 at time step t equals to 3. This is another phenomena called fusion, where you have two mitochondria 1 and 2 at time step t equals to 1 will move towards each other and fuses to give us a new mitochondria 3 at time step t equals to 2. This mitochondria moves forward, making sure we don't get back 1 and 2 again. Fusion. There is a mitochondria 1 at time step t equals to 1, which breaks into two mitochondria and moves separately, giving us mitochondria 2 and 3 at time step t equals to 2. This application brings an interesting problem statement where we can classify the inputs as base feature, features which are available for all the time instances, like nucleus is always available in a cell. Auxiliary feature may or may not be available for any time instances. Characteristics of auxiliary feature are missing data, that is, data for some time instances are missing, and prior information is available for the feature. For example, in touch and run case, mitochondria 1 and 2 is missing in time step t equals to 2, but available at time step t equals to 1. Missing feature. Prior knowledge about their existence or distribution may be assumed. If we know in touch and run case that 1 and 2 are going to touch each other, we can assume the distribution of mitochondria 3. Obsolete features. Features ceases to exist after some time. In the fusion case, feature 2 and 1 become obsolete from time step 2. Sudden unknown features. No prior knowledge of their existence is available and they arrive late unannounced. In the fusion case, mitochondria 2 and 3 arrive suddenly at time step t equals to 2. Unknown number of features. No information about the total number of auxiliary inputs. A cell can have thousands of mitochondria and we don't know how many at each time step. Aim. To design a model that can handle the data stream of base and auxiliary features. So any input feature can be seen like this, where you have a base feature and auxiliary feature, and at each time step, base feature is always available and auxiliary feature may or may not be available. The autonomous vehicle can also be classified in this kind of problem statement, where the sensors of cars can be considered as base features like LiDAR or weather sensors, and the environment around the car, like pedestrian, trees, can be considered as auxiliary features. Previously, deep learning approaches have been proposed for online learning, but they assume that the dimension of the input data is fixed. Some incremental learning approaches were also proposed using ensemble of networks, but these methods are impractical in our case where the input features are so inconsistent. Howe et al. Proposed ML approaches for dynamic environments. However, they assume the dimensionality of the input is constant in batches, and therefore batch-wise learning can be used, but we train after each instances. Using imputation with online learning methods will only handle the missing data part and not the other cases as shown in our problem statement and the diagram here, where Aux-Net is our model which handles all the characteristics, whereas online learning models like ODL and the impute-based model handles some of the characteristics, provides partial support for some other characteristics, and cannot handle most of the characteristics. We present auxiliary network which learns in the presence of inconsistently available auxiliary inputs. The block diagram of Aux-Net is presented here, where the base features and the auxiliary features are handled separately via base module and auxiliary module respectively. The Aux-Net architecture is presented in figure A, where each module has one or more layers. A layer takes inputs as h, z of z minus 1, t, which can be base feature, auxiliary feature, or the outputs from any hidden layers. Sigma is the activation function, and when we apply sigma on this h, we get the output as z of z, t. Each layer is attached with a classifier which takes h, z, z, t as an input and gives an output prediction. This prediction is then multiplied by the importance parameters of the layer and is passed for the final prediction. We update the importance parameters based on the hedge layer by comparing the ground truth and the prediction from the classifier. Let's look at all the modules separately. Base module gets inputs as base features and the ground truth. It gives a prediction and the hidden outputs are passed to the next layer and so on. The middle module has only one layer, which gets the input from the last layer of the base module and also gets ground truth as an input, gives a prediction, and the hidden output is passed for further calculation. Auxiliary module is scalable and agile, meaning that we can add or remove auxiliary layer depending on the auxiliary inputs available at time instance t. It also works similar to the other layers. Now we see the normalize and concatenate components. The normalize component takes the importance parameters of the auxiliary layers and the middle layers and normalizes it to get gamma parameters. The outputs from the hidden layers of auxiliary module and middle module is multiplied by gamma parameters and is concatenated. The concatenated vector is then passed as an input to the end module, and the end module works similar to base module. The final prediction is given by multiplying the predictions of each layers with their importance parameters and summing them up. The final prediction ft and the ground truth gives us loss. We apply OGT to update the parameters of each layers. Let's see the working of Aux-Net. So there can be two situations. First, an auxiliary feature may not appear. Second, a new auxiliary feature appears. When an auxiliary feature may not appear, for example, the first auxiliary feature, then we just freeze this layer. If a new auxiliary feature appears, then we add a new layer and initialize weights and importance parameters for that layer. After, based on the auxiliary features received at time instance t, we normalize the importance parameters. We use normalized components to get the values gamma from the importance parameters of auxiliary layer and middle layer. We concatenate the hidden outputs from auxiliary layer and middle by multiplying with their respective gamma values. The concatenate vector is passed as an input to the end module, and the final prediction is given by multiplying the output of each classifier with its respective importance parameters and summing them up. We update the parameters based on the final loss and each classifier loss. Then we normalize all the importance parameters again for the next time instance. Since standard suitable dataset is not available, we use publicly available time series dataset called Italy Power Demand dataset, which has 1096 instances and 24 features. We transform these to suit our problem. For this, we fix some features as base features and the rest as auxiliary features. The availability of each auxiliary feature at a given time instance is modeled as a uniform distribution with probability P. The same value of P is used for all auxiliary features, but the availability of each is computed independently. We compare our model with ODL, considering only base features since no model can handle auxiliary inputs. Let's see some experiments. Varying probability of the availability of auxiliary inputs. Here, the first 12 features are considered base features and the rest 12 features are auxiliary features. The P ranges from 0.5 to 1. We compared with ODL with 12 base features. The first diagram is of cumulative average accuracy, the second is of cumulative average loss, and the third is of the code snippet. Here we can see that Aux-Net is sensitive to P. As the value of P increases, the performance increases since the amount of data increases. Agile adaptation of Aux-Net in the sense that, say when P is equals to 0.8, 20% of the time auxiliary features are not available, still the loss goes down. The loss decreases and the accuracy improves over time, and as compared with ODL with 12 features, the loss is less in almost all the situations. Varying number of base features. Here, we plot the loss of Aux-Net as a function of the number of base features P and ODL trained using only base features. The probability of the availability of auxiliary inputs is fixed at P equals to 0.9. The Aux-Net is extremely scalable in the sense that even when the number of base features is equals to 1, meaning auxiliary feature equals to 23, the model performs well. However, Aux-Net performs poorer than ODL when number of base features is from 20 to 23, since the cumulative importance parameters of auxiliary inputs is less than the importance parameters of the middle layers as compared to the other cases. Obsolete features. Here, the first 12 features are base features, and the next 12 features becomes obsolete after 100 instances. We compared Aux-Net with ODL with 12 features and ODL with mean imputations. Since we have prior, we can do the imputation. In this, we can see that Aux-Net performs better than ODL and imputation. In the case of certain unknown features, the first 6 features are considered base features, and the next 18 features are considered auxiliary features, which starts appearing after 200 instances. Since there is no prior, we cannot do imputation. Here we can see Aux-Net performs way better than the ODL. In conclusion, deep learning model from streaming classification cannot handle inconsistently available inputs. We present Aux-Net to deal with intermittently available inputs in an online setting. Aux-Net is scalable since it supports for the situation ranging from no auxiliary input being available to all auxiliary inputs being available. Aux-Net is agile since it can dynamically invoke the relevant knowledge model without making the network unstable or unadaptive. Aux-Net is stable due to its importance parameter gamma, which automatically adjusts the contribution of base inputs and the currently available auxiliary inputs so that neither the new auxiliary feature introduce inordinate instability nor are they suppressed. In future, we want to create suitable large data sets from mitochondria simulation and autonomous car simulation and apply Aux-Net on them. These are some of the references. Thank you.